So now we're going to talk a bit about diffusion. So we've got reaction equations, and that will be kind of simple. Now we're going to talk about diffusion. So diffusion is this sort of random motion of particles in air. So it's governed by the heat equation. So if C is the concentration of some chemical, so imagine we've got some tube here, because it's only one dimensional, we're only going to consider 1D here, and into that tube we drop, you know, some sort of spike here of, we put in some dye, and over time, randomly, it's going to smear out from being that. Later on, it's going to look like that, smeared out in the tube. Okay, so this is the direction x, and so our equation is dTc is equal to this diffusion constant times d squared c, okay, which in our case is just the x squared of c. Okay, in 2 dimensions it will be the Laplacian. So this is the heat equation or the diffusion equation, they're the same. And sometimes this in the heat equation, this is called the diffusivity of heat. Okay, so that's the heat equation. You know how to solve this. It's the first equation you solved in PDEs. Or something similar to it. So we can use our Fourier transform, our friend, to solve it. So if we take the Fourier transform, we've got no boundary conditions here. It's going out to infinity here, to plus and minus infinity. Just imagine that for the moment. Which is not how you originally met the heat equation, I'm sure of that. Okay, so take the Fourier transform, we get dt of c hat is equal to minus k squared d of c hat. So we can immediately solve in Fourier space and get c hat is equal to c hat naught times e to the minus k squared dt. Alright, and we can write down the solution here, c naught. This thing has some initial conditions here which I'll write in, right? So maybe give me use purple. So we have c, when t is equal to 0, is c naught of x. Okay, so c hat here is the Fourier transform of c naught. So we know that the inverse Fourier transform of two functions is the convolution. So c of x comma t is the convolution of c naught of x. This is the symbol for convolution with the inverse Fourier transform of e to the minus k d squared d. Okay, and we can look this one up in the table or something like that. So remember that the convolution is the integral. You write that down as well. Convolution of so we've got f star g is the integral from minus infinity to infinity of f of t minus or x, if you want to do it in x. Okay, so we're going to do x minus reaction diffusion equations now. G of x prime, dx prime. Okay, and you can swap this around. It doesn't make any difference. Sure. Okay, so that's going to give us here c of x comma t is equal to. In this Alright, so the chemical modelling of chemical reactions with diffusion, which means the particles can move. So it's quite a beautiful area. It's quite a beautiful topic. It's one of my favourite part of the course. It's not as tricky as the KDB, and we can tackle it and attack the problem numerically, find travelling wave solutions, and all this stuff. Okay, let's get started. So first of all, we've got a bit of chemistry here. So we start with simple decay. Oh, right. So that's the solution here. You could compute. We're not writing down chemical equations, right? You could just simply take the. So we're trying to just write down some mathematics and models it. So it's maybe not quite like inverse Fourier transform. Right. So we would just take our initial condition, Fourier transform with our FFT. PB concentration multiplied by e to the minus kd squared dt, and then inverse Fourier transform of P. But there is this formula here. P and A little a is the concentration of big A.